it going, everyone? Okay, that's enough of that. Hopefully you can see me. I think there's a bit of a delay. So let's get started. How is everything going in the chat? So, hope everyone's having a good day, or a good night, good evening, or a good morning, wherever you are. So, over the past 7 episodes, just 7 weeks, wow, that's a long time. I've been working on an NMyGen version of a RISC-V processor. That's not on an FPGA. I don't know if it's ever been actually done before or completed before, but this is the task that I've set myself to doing. So thanks for watching. And for this stream, oh yeah, that's my humidifier, and that's my cat. Nothing's burning. Okay, so for this stream, basically what I'm going to do is I'm going to take a small bit of the NMyGen code and turn it into an NMyGen version of some actual chips, which will start basically creating the hardware for me. So if you want to know more about NMyGen, look down below in the description. I've put together a tutorial. I've put together some nice exercises starting from 0 to get you familiar with the NMyGen concept and what formal verification is all about. So yeah, why don't we get started? So let's go and take a look at some code. So let me see. All right, yeah. So this is the part of the processor that decodes an instruction into its component parts. And by the way, there seems to be about 30 seconds delay or so between me speaking and the chat. So if you're in chat and you're asking a question and you don't hear from me for half a minute to a minute or so, that's probably why. So the goal is to put the magic smoke into the hardware. Yes, sure. Okay, so this is the section of the code. Rust embedded. No, sorry, I'm not into Rust. So this is the section of the code that breaks apart an instruction into its component parts. Now, some of the component parts are not actually used for some opcodes. Like, for example, for like a JAL instruction, you don't have a destination register, or maybe you don't have an RS2 register or something like that. Func12 is only used for system privileged instructions. So you've got the opcode, which is 7 bits, which is always the lower 7 bits of the instruction, and the lower 2 bits of the instruction are always 1, 1. And that is, why is that? I think that is because that is what the non-compressed instructions are. So anyway, so RS1, that's source register 1, source register 2, destination register. Funct3 is for the ALU operations along with Funct7. So that's why the ALU func is there. And Func12, again, like I said, is for some of the privileged instructions. So this is just, straightforward wiring. The interesting thing that I want to tackle today is decoding the immediate value out of the instruction. So if we take a look at that code, we can see that it actually depends on the format of the instruction of the opcode. So there is this immediate format, which are things like opcode immediate, so where you add an immediate value to a register. The immediate value encoded in the instruction is a signed 12-bit value. So you take 12 bits out of the instruction, starting from bit 20, you turn it into a 32-bit signed, and that's the immediate value. S is for store. R is for register instructions, so of course there is no immediate. So I just set it to 0. What was U? I think U was just unsigned? Yeah, unsigned. So you take a bunch of bits out of it, I think it's 21 bits, and you just stick it in the immediate value, so effectively it's 0 extended. Opcode format B are the branch instructions. And if you're wondering where all these opcode formats come from, you can look at the RISC-V specification. Again, there's a link down below. And that specification shows the formats of the different instructions. And basically, it lists out the format for I, S, R, and so on. So branch, it's a lot more complicated because the bits are sort of, shuffled around in the instruction, and you have to sort of unshuffle them and put them together. So that's why it looks a little more complicated. But again, the bits are all there. There are 13 of them, and it gets sign extended. So that's a branch. With the jump, there's actually 21 bits. Again, the bits are all over the instruction. And you have to put them together and then sign extended to 32. And then finally, we have some system opcodes, and these are the CSR instructions, so things like reading and writing, setting bits and clearing bits in CSRs. Those are control and store registers. There are only 5 bits, so there's not a whole lot there, and it's also 0 extended. So. All right, what should you learn? NMyGen, Verilog, Embedded Linux, Rust, RTOS, not to mention hardware. Well, I don't know anything about Rust, so you can learn it or you don't have to. Embedded Linux, I mean, I can use Raspberry Pis, but, I don't program the operating system. RTOS, again, I don't program the operating system. Verilog, I've used and I didn't like it, and that's why I went to NMyGen. So what should you use? What should you learn? NMyGen and Yosis. That's pretty much what I exclusively use. I no longer use Verilog or VHDL or anything like that. It's all NMyGen. Yeah, okay, so WebAssembly. I don't know anything about WebAssembly other than that it's nice, and there is actually a WebAssembly version of Yosis that was put together, but I don't use it. So anyway, okay, so this is the function that I would like to convert into hardware. So let's take a look at KiCad. Let's see, I want to drop this. Yeah, here we go. Okay, so here's some KiCad for what I think the circuit is gonna look like. So it may be a little small. Let's see if I can zoom in on that. Okay, so the idea is that, like the function, let me just pull up the code again. So the function basically depends essentially on the opcode format, right? And every opcode decides what the opcode format is. Will this stream be available for offline view later on? Yes, it will. It will be a permanent part of the record, unfortunately. You've never used NMyGen, and what is the difference between that and VHDL and Verilog? Okay, so VHDL, Verilog, and NMyGen are all high-level hardware description languages. What VHDL and Verilog are, Verilog is, I think, based on ADA, and VHDL is based on C. And they are their own special language. So you have to know all the ins and outs of VHDL and Verilog. And typically when you get some software from an FPGA vendor, they will accept one or both of those two. NMyGen is sort of like, well, if you're familiar with Python, you can use all the Python goodies to generate some HDL code. The HDL that NMyGen spits out is called RTLIL, which is Register Transfer Language, Intermediate Language, I think. And that can be ingested by Yosis to program FPGAs or whatever. It can also be translated into Verilog, which you can then use on your own FPGA vendor's software. So, and the reason that I like to use NMyGen is that it's Python, and I like Python. And if I need to generate code, I know how to do it because I know how Python works, and it's fairly straightforward. It's a general purpose language, unlike something like Verilog and VHDL. They try to be a general purpose language, but they pretty much fail miserably at that. That's my opinion, and that's where we're going to leave it. So, okay. So anyway, what I was saying is that the decode of the immediate value pretty much depends exclusively on the opcode format, which is determined exclusively from the opcode. And then the rest is just shuffling the bits of the instruction around and either sign extending or zero extending, and that's how you get the 32-bit immediate value. So the circuit that I want to create takes in the instruction and the opcode format, or just the opcode, and it spits out the immediate value. So here is the circuit again. So we can see here that the input is the instruction. This is the 32-bit instruction. It's the raw instruction that comes from memory. What's the yeah, that's my humidifier. I have a feeling that I'm going to explain that quite often because it does look like smoke. Okay, so you've got the instruction, and also down here you've got the opcode coming in. Now, yes, the opcode actually does come from the instruction itself. So I could just, tear off those bits out of the instruction and stick it right in here, but I felt that just for readability, it would be nice to break out the opcode into its own special signal. Okay, so there are a bunch of different opcode formats. So here's the circuitry that'll take care of the I format. This is the S format. This is something I'm calling upper, which I guess is U. There's also B and J and the system. Now each of these, we go into them. So what I'd like, oh, great. Okay. So what I'd like you to think of this section as is a multiplexer. And the idea is that we are decoding the immediate value for all of the instructions, but we're only letting through the immediate value that is appropriate for the opcode. So that's why I have this, let's just call it a selector, and it selects one or zero of these 6 values, and then they all get tied together because it's a multiplexer. Now, what is one of these look like? Well, it's basically a bunch of 32-bit buffers. So these are 74 FCT 16244s, which are 16-bit buffers. They are arranged in groups of 4 that can be controlled independently with an output enable signal for each one. And I've got 2 of them because I need 32 bits. So this is basically a 32-bit buffer. Now, the interesting thing is that if I turn off the output for this buffer, then the output goes high impedance, which means that I could tie a whole bunch of buffers together, turn one of them on, and then I could turn it off and turn another one on. And that's basically a multiplexer. Okay, do I think Logisim is suitable for teaching a digital logic introduction? I have never used Logisim, so I can't answer that question. Sorry. Okay, so the buffer is pretty interesting. Let me see if I can pull up the data sheet on that. Okay, so here is the data sheet. So the worry about buffers, when you've got 2 buffers with their outputs connected together, is that when you turn one of them off and the other one on, there's a danger that they'll both be on for some short period of time. And the thing about buffers is that they can source a lot of current. So if 2 buffers are on at the same time, that's really bad because they're probably going to burn. The thing that I like about the 16244 is that if we go down to the timing, we can see here the output enable time and the output disable time. And the nice thing is that the output disable time is always at least faster than the output enable time, which means that if I turn one off and the other on pretty much simultaneously, I can pretty much be guaranteed that the output will be disabled before the output of the other one is enabled, which means that they won't conflict with each other. So that's why I think I can use these effectively as 32-bit multiplexers by simply tying them together. So if we go back up one level, we can see that we've got these 32-bit buffers all with their outputs tied together, and one of these is only one of these is going to be selected, or possibly 0. In which case the output is going to be high impedance. So I should probably have some pull down resistors of some relatively high value, just to make sure that the output is 0 if none of these are selected. Because the thing about modern CMOS and even TTL is that if you have an input, you need to make sure that the input is not high impedance, that it has a specific logic value. Otherwise, the input internal to the chip is going to float to some halfway value, and it's going to burn a lot of current. So if you ever run into a situation where it's possible for a bus line not to be driven, and that bus line goes to some inputs, well, make sure that you put pull-up or pull-down resistors on them. So. All right. What about the NOT gate delay? The NOT gate delay. Yeah. That I think what you're talking about is the NOT gate from internal to the buffer. If that's the case, well, the timing data sheet, the timing in the data sheet is basically from that input to the output. So that includes the NOT gate delay, if that's there. Targets for the clock speed, yeah. So if you've looked at the previous videos, you'll know that I have a system clock, a machine cycle, and an instruction cycle. Basically, the system clock is the fastest clock. The machine cycle is 6 system clocks, so I basically have 6 phases, and that forms one machine cycle. And then there's the instruction cycle, and instructions can take anywhere between 1 and 3 machine cycles. So converted into system clocks, an instruction can be anywhere between 6 and 18 system clocks. I'm hoping that I can get a system clock up to 10 megahertz. That would be nice. It's never going to be fast enough to run, like Linux or anything like that, but I don't care. I mean, I'd like to program like it's 1985 again. So there you go. Okay, so anyway, we can see that shuffling the instruction bits around is just a matter of wiring, right? Because all of these are buffers. You just route the instruction bits to whichever bit is appropriate in the buffers. And then you select whichever buffer is appropriate. And if we take a look down here, this is the selection logic. So here's the opcode. It's 7 bits, and that goes into a generic array logic chip. So a GAL 16V8. There's also the ATF 16V8, which is still being sold. These chips have been in use since the early 80s, if not prior to that. Can't you have one selector active and simply ignore the immediate bus? At least it won't be Z. No, because in the circuit, the immediate bus does go somewhere. It may go to a multiplexer. It may go to another multiplexer where the immediate value is simply not selected, in which case you would say, well, then why does the immediate bus even matter? Again, it goes to the input of a chip somewhere. And the chips respond very poorly if their inputs are high impedance, which is why you always want a pull up or a pull down. So that's pretty much why. Oh, can't you have one selector active? Ah, yes, okay. I could, I guess. That's definitely a thought. Yeah, I misunderstood that comment. That's definitely an interesting thought. So instead of, for example, the system immediate value being just for the system opcodes, I could make it for every opcode except the ones that I've already decoded. That's an interesting concept. I'll have to think about that and see if it actually makes sense. It probably does make sense because, yeah, the immediate value would not be used by the rest of the circuit. Good idea. Thank you very much. Okay, so the GAL. So this is basically generic array logic. I'm not using its register capacity. There are registers on the output that you can bypass. Really, it's just a sum of products. So it's basically a bunch of ands and then tied together with ORs. And this is what the logic is going to look like. These are the opcodes that we have. So I consists of, let me just take a look at what those opcodes actually are. So I is load, miscellaneous memory, which I actually don't use, and opcode immediate. S is for store, U is for upper. U stands for upper, and that's the AUIPC and LUI instructions. B is for branch, J is for JAL and JALR, and then of course system is for system. So yeah, okay. So what I want to do is I want to get started by essentially, let's go back to the code, and we can see in the sequencer card that what I want to do is replace decode immediate with its chip equivalent. Okay, so we know that we're going to need some 74 16244s and a GAL. And of course, the GAL is just going to be some logic. It's not going to be a quote standard chip because it does have to be programmed. I could replace it with a bunch of gates, but then it would be messy and stupid, and I hate it, and my life would suck. So Let's go ahead and write some code to simulate a 74-16-244. The idea is that when I replace the decode immediate function, when I replace the insides with an equivalent that uses the chips logic as modules, I should just then be able to run formal verification, and it should just work. So let's try that. So what I'm going to do is create a new file, and I'm going to pull up just my standard stuffs, standard header, and all the NMyGen stuff. Okay. And I have a skeleton somewhere, but I'll just sort of steal it from here. And I'm going to call this IC7416244. Contains logic for a 74-16244 16-bit buffer. Okay. I don't need that, and pass for now. And then we know that there is an elaborate function. Sequence record. Oops, that was dumb. Okay. Yeah, save as IC 7416244. Okay, now I need an elaborate function. Where's elaborate? Oh, I just had it. Okay, and that's turn M. Okay, so that's the skeleton of implements the logic of the buffer. Okay, so that's the skeleton of an NMyGen module, basically. Again, if you're interested to know exactly how to get started with NMyGen, there is a series of exercises. Look down below in the description for a link to those exercises. Once you've done those exercises, you can look at the tutorial, and there's a lot more information about all the different things you can do with NMyGen over there. Okay, the 16244 buffer is not in the official KiCad library. Yes, I've thought about adding it. However, right now I believe we're in the transition between KiCad 5 and KiCad 6. And they've changed the format of the libraries. So the problem is that if I go ahead and create the symbol and then check out the code from the official sources, they, I believe, want me to have a pull request against the current nightly version, which of course is KiCad 6, and I'm using KiCad 5 because I'm a little too afraid to use the nightlies. KiCad 6 is not yet released. So basically we're stuck in a kind of holding pattern until they release KiCad 6 and the new version of the library comes out, the new format. So yeah. All right. Let's see. Okay, so what I want to do, first I want to define my signals. So if we look at the data sheet again, let's see what we've got. Actually, why am I looking at the data sheet? I've got it in KiCad. Okay, let's go into one of these buffers. Okay, so there it is. So the idea is I have 4 groups of 4. Okay, and they're called A. So what I'm going to do is for my signals, I'm going to have A0 equals an array, that's an n-mygen array, so let me just make sure that I have that, of signal, wait a minute, why am I doing that? It's just a 4-bit signal. Okay, and there are 4 of them. I'm not going to bother making this an actual array. I'm just going to enumerate them. Okay, now we have negative output enable 0, negative output enable 1, and 2 and 3. And these, of course, should all be self. Self, 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 self. Okay. And then we've got the outputs, which are called Y, and those are also 4-bit signals. Oops, caps lock is on. Okay, those are the inputs. So inputs, output enables for each section, and outputs. Now, I suppose I could make a submodule. In fact, why don't we do that? So I'm just going to do this, sub. So this is a 4-bit buffer. And I'm just going to say that the input is self.a. Because these are just independent, negative output enable, and Y is signal of 4, okay? So instead of having all this, which we don't need anymore, okay, so let's just define the 4-bit section. Okay, let me just check the chat. How are things going in chat? How's chat going? Everybody doing good in chat? Looks good. Okay. So, what we're going to do is, okay, now again, I've explained this before, but I will explain it again. You can paste in column select mode. Alt-Shift. Really? Alt-Shift. Oh. That's pretty cool. Thank you for letting me know. Are chip timings relevant? Okay, so the unfortunate thing about a design language like n-mygen is that typically they're targeted towards FPGAs, and you don't really worry about the timing except you use good practices. I suppose I could simulate things like delays by having a system clock that was half a nanosecond, and then I could actually, write these chips so that there's a delay between the input and the output based on these clocks. I could do that, but honestly, what's the point? As long as I keep in the back of my head the timing requirements, I think it'll be fine. So, yeah. Okay, so what I've said before is that n-mygen can't do high impedance signals. So signals are either 1 or 0. So the typical way that you put together 2 high impedance signals is you output zeros on the signals, and the bus value is just the OR of all of the output signals. That way, if none of them are on, the output is 0. And of course, I guess you would assume that in real hardware you would have pull downs. But if one of the outputs goes high and all the other outputs are 0, when you OR them together, the result on the bus is just that one output. So that's what we're going to do here. So the first thing we're going to do is combinatorically y is equal to 0. So by default, we just output 0. Now, if self.noe equals 0, because this is a negative output enable, y equals a. And that's it. That's a 4-bit buffer. Okay, so now, because the 244, 16244, a test bench, yeah. I do not believe in test benches. So what you call test benches is what the software world calls unit tests. Unit tests are great if you want to test 1 or 2 scenarios. However, with hardware, I typically use formal verification, which is a lot better than unit tests because formal verification tests all possible scenarios, not just the 1 or 2 that you can think of. Now, yes, you could design a test bench with delays in it, but again, as long as you keep in the back of your mind the timing requirements, I think it'll just be fine. So, all right, so this is our 4-bit buffer. Now let's create a 16-bit buffer out of that. So what I can do is I can say self dot I guess I'll call it 0, equals signal of, or should I make, yeah, okay, signal of 4, sure. Self.A1 equals signal of 4, and so on. 2, 3, okay. Now we've got the negative output enables. Why did I get rid of those? I needed those. 1, 2, and 3, and Shift Alt Y. Nice. Okay. Yeah, self is kind of like the this keyword in Java, for sure. Okay, is self y equals 0 high Z or output is driven to low? Output is driven to low. And again, like I said, this is appropriate when you want to output high impedance, but you're outputting it onto a bus. 0 ORed with anything is anything. So just like an output combined with high impedance is that output. So logically it works out. Okay, so we've got submodules. So m.submodules plus equals, let's see, I'll just call it S for section 0 equals this. Actually, I think I need to do this. 1, 2, 3. And then I can just say S0, S1, S2, S3. Okay, so these are the submodules. What tool chains are you using for formal verification? I'm using Yosis. So again, if you check down in the description below for the NMyGen exercises, you can follow along and learn how to use NMyGen and then learn how to use the formal verification engines for Yosis to do formal verification. So. Okay, just joined. We simulating design base? Yes. Well, no, we're not simulating it. We're actually building one. Again, this is a RISC-V processor that is not being built in an FPGA. It's just regular logic components that you can buy off the shelf, except for FPGAs, because I don't want to do that. And we've already written all the logic. If you check the past 7 episodes, that's what that was all about. We formally verified it to ensure that it works. And now we are replacing bits and pieces of the higher level code with essentially lower level gates or chips. So, and then we're going to run the formal verification again and make sure that it works. And if it does, we can be pretty sure that when we build the circuit, it should work, modulo the timing requirements, as I keep being reminded. Okay, so we've got these submodules. Now we just need to hook up the signals. So in the combinatorial domain, because there's nothing synchronous going on here, so S0 dot A equals self.A0. So we're basically just wiring our input. Just say inputs, output enables, output. So we're just wiring our inputs to each of the signals in the sub-circuit right here. So there are, of course, 4 of them. 1, 2, 3. Okay. We're also going to want to do the same thing for the negative output enable signals. So I can do this, and I think this. Yeah. And this. Okay. Great, that's our output signals. And now, that's our output enable signals. And now we have to wire the outputs back to the outputs of this module. So that would be self.y0 equals S0 dot Y. 1, 2, 3. 1, 2, 3. Okay, does that look right? I think it looks right. Let's write some formal verification code to make sure that it actually works. All right. So, writing some formal verification code. Let's go down to a class method. I don't know why there's a space there. Stick a pass in here to appease the linter. And let me also grab the main so that I can run this thing from the command line. Okay, so for formal verification, what I do is, where is it? So I start off with the module. So with formal verification, you're basically, creating a module, just like you're creating a module for your module thing. And also, I return 2 things. I return the module and the signals that we're going to manipulate in order to test. So the first thing I need to do is create an instance of the thing that I'm going to test. So that's this right over here. And then I need to add it to the list of submodules for this module. Okay. So now I can refer to S and I can say that the inputs that formal verification is allowed to manipulate are S.A0, S.A1, S.A2, and S.A3, and also the output enables. NOE0, 1, 2, 3, 3, 2, 1, lift off. Okay. Okay, and now we need to write what we want to always be true. So here are a few things we want to be true. If negative output enable is equal to 1, assert that y0 is equal to 0. And I guess we're going to just copy that. 1, 2, and 3. Actually, I don't need the equals 1 because it really is just one bit. 1, 2, 3. Okay? And there's an else part. Else s.y0 is equal to s.a0. Okay? So now again, you might think that this is kind of ridiculous because you can just run through all 32 combinations and you're done. Oops, I forgot the colon. And that's true for this really simple circuit, but this is kind of a different way of describing exactly all the 32 different input combinations. And yeah, I know, so much boilerplate. Welcome to programming. So I could check all 32 inputs, but all 32 combinations. But what if you had a 32-bit input? I mean, you're not going to check all 4 billion combinations. That would be ridiculous. So that's why you write it like this. And again, you know, for something simple like this, it doesn't really look all that different from writing a unit test to check all the combinations. But again, when you get to more complicated things, you just can't write unit tests. Okay, main is missing. That's because main is in util. So let's go ahead and stick that in there. How's that looking? That's looking pretty good. All right, so the first thing I'm going to do is try to compile this. So let's take a look at the command line. Okay, so Python 3, IC 7416, that thing, gen. And let's hope it works. It works. Okay, it compiles. That's great. So now let's create the symbiosis file. So let me go grab a simple one. This is fairly simple. Let me copy it to, I'll just copy it to IC. It's probably going to be used for all the ICs. Oh wait, I already have one. I called it ICs. Okay. Well, let's do that then. All right. SBY minus F ICs.SBY. And we're going to run it in BMC mode, and it passed. Okay, well, that was anticlimactic. It works. Well, okay, well, we know that all of these properties are now true. They hold. So it does what it's supposed to. Let me just double check that I got these negative output enables correct, because, you know, inverting signals is really bad. That last line is not visible on the stream. Thank you. Okay. Yeah. So let me go ahead and pull up the code again. Okay, so we know that all of these properties hold true. And that's that. So now let us go ahead and try to use it. Can we use it in decode immediate? Okay, can we do this right now? No, we are not going to use this right now. We're going to create that gal. Okay. So for the gal, This is going to be just another module, so I'm just going to copy this and call it gal immediate format decoder. Okay, so probably won't need this. And this is just going to implement the logic that I'm going to program into that gal. So this is IC gal immediate format decoder. Okay, so the input is self.opcode, and that's a signal with how many bits? 7? 6? 7. And that's it. The outputs are going to be the different negative output enables. So there's one for I, negative OE. Let me just check my circuit. Go up one level. Okay, there we go. So I need SU, BJ, and sys. So let's go back to KiCad. SU, BJ, and sys. So those are our outputs. So the logic is going to be so in fact I wrote the logic here. Let's see. Well, let's deal with sys first. So 111 0011. So 1111. Actually, I can just copy this from the other window. Just give me one moment. There we go. Okay. So there's the logic. So, plus equals. Okay, so self.I NOE is equal to not of self.opcode. Actually, you know what? I can make that a switch statement. Switch on opcode. For 0B, let's see, for this, oh, sorry, very sorry. Okay, so what I did was I copied the logic out of KiCad that I had in there. So here's KiCad. I copied that into the code as comments so that now I can write the logic. So we have a 7-bit input signal, which is the opcode, and we have the outputs, which are the output enables or negative output enables to the buffers. Okay, so for these cases, a gal is not exactly a lookup table. It's really a sum of products. So you have the input signals, and then you AND some of them together. You can also AND the inverse of those signals together. And then you can OR some of those ANDs together. And there's usually a limited set of OR terms that you can have per output. Gals are typically registered, so they have registers on the output that you may use if you want to, or you don't have to. There is internal feedback in that you can include the outputs as input terms as well. So they're very useful little glue logic chips. Unfortunately, they've kind of been superseded by FPGAs because everyone wants to stuff everything into an FPGA, not just glue logic. So, but they're still being manufactured. So there you go. All right. Let me get some defaults here. So m.b.combinatorial equals self INOE equals 0. and I'm just going to repeat that for all the others. S, U, B, J, and sys. Okay, so that sets, that should be 1. So by default, they're all off. Okay. For these cases, self.i.noe equals 0. Okay, and then I just do the same thing for all the others. This is pretty much where, if I were in a real video, I would edit this out, but we're doing this live. So just copy a bunch of these. Here's U. U, B, J, and sys. So the thought was that I could actually make this a default. Why don't we just do that now? Why not? Okay, so let's see, B is this. J are these two. And that's the default. That's really it. Okay, do I really want to formally verify this? No. After all that philosophizing about how great formal verification is, I'm not really interested in formally verifying this chip. We'll formally verify it when we replace it in the sequencer. All right, let's go ahead and replace this. So, first of all, what I'm going to do is I'm going to create in the sequencer card chips. Chips is a Boolean that defaults to false. So the idea is that here I can say self.chips equals chips. And then when I create a sequencer where chips is true, then it will generate the code using chips. Okay, what other tools have I used for development? Is nmygen the best you've used? Okay, well, I haven't used all that much. I've done a little bit of VHDL and I've done a little bit of Verilog. And I got really annoyed at it because, well, it's a new language and I hated it. I didn't like Verilog because it was very ADA-like and I never studied ADA. And I didn't like VHDL because it was just enough like C to be annoying. So I decided to look at alternative HDLs, so-called new HDLs, and nmygen was the one that I liked because it was Python-based. So, okay, where was I? Right. So I now have this Boolean that I can set when I create the sequencer called chips. So when chips is true, I can just substitute out all of this stuff. So here's what I'll do. If not chips, that's all this. If chips, I'm just going to call self.decode im with chips. I didn't have to do that. I could have just returned. So get rid of all this. And just replace that. There we go. Because remember, nmygen is a generator of code. It's not the code itself. if self.chips. Okay, so now we need to define decode im with chips. Right. So, decode im with chips. So, what we're going to want to do is create submodules. I don't know if this is going to work, but what I want to do is create two instances of the IC. So there's IC 7416244. Actually 12 of them. Yeah, 12 of them. So buffs equals for I and for nothing in range 12. So now I have an array, a Python array, not an NMyGen array, a Python array of these things. Okay, and also I want a gal equals IC gal im format decoder. Okay, I need to import those. So from IC74 this import IC that from IC gal import IC gal. I'll probably end up just putting all the gals in a single file so that I can just do from IC gal. But, you know, for now, I can't be bothered. All right. Where is... Okay. And m.submodules plus equals gal. Okay, so those are the submodules. So now what I want to do is code this according to the circuit. So, oh boy. Oh boy, oh boy. How do we do this? Okay, well, the first thing I could do is I can hook up the gal signals. I know how to do that. Right? So I have self.opcode. That's just one of the signals that exists in this module. So what I'm going to do is say combinatorically gal.opcode equals self.opcode. Done. And then I want to route the outputs. So let's see, buffs of, okay. Let me make some intermediate signals first. So let's do INOE equals signal. So we have I, S, U, B, J, and sys. So what I want to do is grab, it's because this is in state. Is it in state? Oh, did I not make opcode publicly available? I'll fix that later. Okay. M.D, oh, it's underscore opcode, right? Because I made it a pseudo private. Okay. So buffs of 0 equals buffs of 0 dot NOE 0 equals INOE 1, 2, and 3. And then buffs of 1, which is the other pair. Okay. Now I need to copy this for the other 6 32-bit buffers. And there is a way to do that. because we're using Python. For I in, well, let's do this. NOE equals this S, U, B, J, and sys. S, U, B, J, sys. For I in range 6. So now instead of this, we're going to say NOE sub I. Copy. Paste. And then instead of 0, it's going to be I times 2. So what I'm doing here, and then this is I times 2 plus 1, is I'm just writing the logic, I'm just writing some Python to create the logic in a regular programmatic way. Okay, and I suppose that if I had these as arrays, I could make it even simpler, but whatever. Okay, so that hooks up these signals. Now I have to say, now I have to route the gal's signal outputs. Gal dot INOE. Is that the right thing? Middle mouse dragging. Oh, middle mouse dragging is even better. Thank you. Okay. S, U, B, J, and sys. S, U, B, J, and sys. Okay, so that's the gal hooked up. So I've got these intermediate signals. Those signals get routed to the 8 output enables. The input, the opcode goes to the input of the gal, and the output of the gal goes to these intermediate signals. All right, what's next? Well, shuffling around the instructions. So I'm going to have to go through each of these buffers. So let's go with format I first. My keyboard is nice and clicky. My keyboard is a DAS keyboard, D-A-S, DAS keyboard. It's got very nice, clicky, and believe it or not, it's not the clickiest that it could be. Okay, so I think that what I'm going to do is, let's show KiCad again. Okay, so here is I, right here. So this is how we split up the instruction for I. So now I'm going to have to think a little carefully about this. So what I want to do is create some more intermediate signals. So I32 equals a signal of 32. So this is going to be the input for the I set of buffers. Okay, because I know that I'm going to screw this up. So S, U, B, J, and sys. So what I want to do is, just like I routed these buffers, I want to route these input signals. So what I'm going to do is something like m.d.combinatorial equals buffs of 0 dot A0 is equal to I32 0 to 4. So that's the Pythonic way of selecting the first 4 elements out of I32. So this is just bits 0 through 3 inclusive, right? And then I have A1, 4 through 8, 8 through 12, and 12 through 16. And then, of course, I'm going to do the same thing for the other 16-bit buffer in the pair, except now this is going to be 16 to 20, 20, 24, 24 to 28, and 28 to the end. Okay, and now I'm going to do the same thing. So sig 30 input 32 equals I32, S32, U32, B32, J32, Sys32. For I in range 6, just generate those things. So input 32 sub I, grab that, nice. And then it's going to be this to that, and this to that. Okay, so that's those intermediate signals. Okay, so now that I've routed input into the buffers, so they've sort of spread out now throughout the buffers, now what I can do is I can put together the inputs. So I can say something like, for format I, let's see, what have we got? So I32, m.d.combinatorial, I32, so the first 12 get the instructions 20 to 31. And then the others from 12 to the end equals whatever self.instruction 31 is. So what I'm doing here is I'm taking bits 20 through 30 inclusive, and I'm putting them in bits 0 through 11 inclusive. So I'm basically taking this set of 11 bits and sticking them in the lower, in the least significant 11 bits of the 32-bit input. And then what I need to do is replicate, because I'm doing sign extension, so I want to replicate this 31st bit into the rest of the bits. And the way to do that in MyGen is using the replicate function, which replicates this for, let's see, 32 minus 11 is 21 bits. Fence post error, right? 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 Yeah, 32, 21. Okay, yeah, sure, fine. Well, I mean, if I have too many bits, MyGen is going to truncate to the correct amount of bits. So I could even make this 32 if I wanted to. But let's do that. Okay, is replicate imported? I believe it. Oh wow. Okay, so first of all, this is state, because that's where I put it. Is replicate in here? No. Replicate. Was there an error that showed up somewhere else? Why is this showing up as an error? does it care? Is that a warning? Unable to import. Oh. That's because it's in, because for some reason I put it in this file. You know what? I'm going to rename this file to just rename ICGal. Okay, that'll make things easier on me. ICGal. The range does not add up for the first assignment. Let's take a look. Do you mean this? You are correct. That's what it should be. Okay, and now it's complaining about I32 because I called it I_32 for some, no doubt, ridiculous reason. Okay, so that's format I. So this is the sign extension. Okay, get it out of your system. Sign extension has a funny abbreviation. So the next format is S. So let's go back to CAD. And we can see that this is how the thing is broken up. So wherever you see, this is how things are being broken up. So whenever you see one bit going into multiple bits, that's actually a sign extension. And if you look at this 0 over here, that's because we're stuffing all zeros into this part of it. So Python likes underscores. I like underscores too. I also like dashes. Dashes are fun. So anyway, so now we want to take care of S. So m.d.combinatorial equals. So now S is S32. That module and plus equals op on it seems like it is actually a monad. Okay. So just a bit of explanation what this actually is. So m.d.comb is actually in the combinatorial domain. It's basically just an array of n-mygen statements. And EQ, when you take a signal, and you slice it, the result is a signal. And when you do dot equals on it, that becomes a statement. So it's basically just an array of statements. Okay, so S32, let's see. So from 0 to 5, we're going to stuff in, local variable. Note that this is not an intermediate signal. This is a Python local variable. So, okay. So this is instruction 7. I could just do this. And again, n-mygen is just going to truncate it properly. So sure, why not just do that? Yes, the video will be saved to the channel. So no worries there. Okay, so from 5 to 11 is instruction 25, starting from 25, bit 25. And then we're going to have a replicate, so S32 from 11 on is equal to replicate, it's actually instruction 31, and replicate it how many times? Do I really care? No. Okay, so that way it'll replicate it out to 32 bits and then truncate it into whatever is assigning to it. Okay, so that's format S. Let's handle format U. This is upper. So for this one, I want to put zeros into the lower 12 bits. So 0 through 12 equals 0. So, I don't have to replicate this because 0 is actually an integer. So, and U32 of 12 and on is just equal to instruction of 12 on. Okay. What's format B? Format B, fairly complicated. So the 32-bit input to the B buffers are 0 is 0. 1 through 4. It's really error prone to translate between inclusive and exclusive bit boundaries. So no doubt I'm going to get something wrong, but anyway, let's see. So this starts from instruction at bit 8. B32, so from 5 to 11. There is actually an alternate way of specifying like beginning and number of bits. There is an nmygen function that you can call on a signal, which will give you back a slice, and you just give it the starting bit number and the number of bits. I think it's called bit select. So you could do, instead of what I just did, you could do bit select 5, 6. And that'll give you 6 bits starting with bit 5, which may be less error prone, but I sort of got used to this. Okay, so 5 to 11 starts with instruction bit 25. Bit 11 is just equal to instruction 7. And bit 32, 12 to 31 is just sign extension. So it's just going to be equal to instruction 31 sign extended. So instruction 31, that's the most significant bit, which is essentially the sign bit of a signed signal. So that's why I'm replicating it, so that, it's sign extended. Okay. Format J. Okay. J32. Okay, let's see. 0 is again equal to 0. S32. So from 1 to 10 inclusive starts from instruction bit 21. This is a J. J32, 11 is equal to instruction 20. J32, 12 through 19 inclusive starts from instruction 12 and on, and then replicate the sign bit into 21. Okay, and then finally we have format Fromont, format sys. So sys32 of 0 through 5 equals instruction starting from 15 and the rest is 0. Okay, those are the inputs. Okay, so let's go back to KiCad, and you can see that what we've been doing is we've been putting together these signals. So these are the inputs to these buffers. So this was all the code that we wrote. We're getting it from the instruction. We shuffle the bits around and we construct these individual things. And previously we wrote code to take these individual signals, these nets, and put them into the buffers. So now, all we have to do now, error in line 692. I'll get to that in a moment. So now all we have to do is hook all of these up together. So, error in line 692. Thank you. Thank you very much. Hopefully I would have caught that during formal verification, and it would show me something. So. All right. So now we have to hook together all of the outputs together, and the way to do that is, okay, so we need to stick them all on self._im. So self._im equals just the OR of all the outputs. Well, I don't have intermediate signal outputs. It would be nice if I did. So let's just say output I32 S, U, B, J, and sys. There is another error on line 692. Another one. I don't see it. This was 692, right? B's, J's. Okay, well, hopefully you can tell me what it is, because I am not really seeing it. Okay, let's go ahead and grab this and just copy it. Call that out 32, and these are the O's. 20 to 21. Let's see. Yeah, that's right. That should be 20. Let me double check the circuit. Format J should be 20 to 31. Yep. Thank you very much. Okay, again, formal verification would have caught that, but thanks for watching. Thanks for watching out for me, because that saves me some time. Okay, these are the output signals. All right, so I can just take this, stick that here, stick that here, and then this is just Y, and then I just need to shuffle these things around. So kind of a pain. Let's see, out 32I, 0 to 4, 4 to 8, 8 to 12, 12 to 16, Y 0, 1, 2, and 3. Hope. you drag selected text? You can, I think. Yeah, you can. Okay, does this look right? Yeah, so this is the first set of 4 buffers. This is the second set of 4 buffers, and I've got my output signals. Okay, so the immediate value is simply equal to all of these ORed together. Okay. Is that it? I think so. So let's just make sure we've got this. So we have 6 32-bit buffers, which translates into 12 16-bit buffers. And then we have a gal. So we add the buffers and the gal to the submodules. So we have some intermediate signals. We've got 32-bit input signals and 32-bit output signals for each of the buffers. And we've got the output enable signals for each of the 32-bit buffers. We route the output enable signals to the individual output enable signals of all the buffers. Same thing with the inputs and outputs. We route the gal, we route opcode into the gal's inputs, and we route the gal's outputs to the output enable signals. And then finally we construct the immediate values themselves and multiplex them all together. All right. So, in the sequencer card, I have this chips Boolean. That's by default false. So in the formal CPU, when I create sequencer card, I'm going to change this to chips equals true. And now I need to run some formal verification. So let's open the command line. All right. So first of all, will it even compile? So I have a make file, and I can select something. So let me select one of the instructions. So what I've done is I've taken the instruction set and I've divided it up into, like easy, medium, and difficult. Difficult would be like the 3 cycle instructions that do loads and stores. And the easy ones are the 1 cycle instructions like AUIPC or LUI. And I've split them up in formal verification so that I can verify just one of the instructions. And I went into the philosophy of why this is done in episode 7, the previous video. The other nice thing about splitting things up is that then I can run them all in parallel by simply doing something like, make -J8, which will run 8 formal verifications, each one on different sets of instructions at the same time. So I'm just going to do this and hope that it compiles. It compiled. It's running. Oh, got a bug. All right, let's see what the bug is. So it failed in 452. So let's go to VS Code and take a look at what 452 is. And sometimes that will give a clue to what the bug is, but if not, okay, 452. So according to this, the result was unexpected. So it looked at the destination register and it saw that the result was not what this was. So the question is, where did I screw up? So let's see if we can try to figure that out. There are a lot of signals, though. Decode in chips. There are a lot of signals. Let's see if we can list them all. So let me start up GTK wave. So GTK wave minus F. This. All right, so let's go to the sequencer and pick out a couple of the signals. So first, what I usually like to do is just display the clocks. Okay, so these are the two phases of the clock. All right, so we have some of our intermediate signals are listed, which is nice. And we've done LUI, which would be a U-mode instruction. So first of all, let's take a look at the immediate let's take a look at the instruction. Let's take a look at the instruction. Where is it? Right here. Okay, so there's the instruction. It's F2 00D0B7. So what's the immediate supposed to be? Do I have result here? I do. Okay, so the result is supposed to be F2 00D000. So that's what we expect. And what we can do is we can also look at the register that it was going to stick the value into. So there's an RD in here somewhere. Okay, so it was going to stick it into register 1. So now I can look at regs after and look for 0, 1. Where's 0, 1? Looks like it put zeros in there. Okay, so obviously I got my wiring screwed up. Let's see if we can figure out which wiring got screwed up. So let's go back into the sequencer. So all zeros is suspicious. That kind of means that nothing came out of the buffers. So the first thing is, did I actually enable the buffers? So the negative output should be U, where is it? U-N-O-E. Nope, it's 1. Okay, so that's definitely a bug. All right, so where is U-N-O-E? That's this, U-N-O-E. So that means that the gal is not galling. So there's the opcode. Let's just take a look at underscore opcode. Underscore opcode 37. Okay, now let's take a quick look at the gal code. Do I have a copy of? I didn't name it. So I don't know which one of these submodules it is. That's okay. Let's see. So by default, it's this. And here's my input, and I expect 3.7. Which one is 3.7? Where's U? That's funny, I don't see 3.7 in here. Did I screw up the table? So this is I. Here, let me just comment on this. I, S, U. Huh. Okay, did I get my table wrong? Let's take a look at Oh yeah, I'm sorry. You're not actually seeing VS Code, are you? There we go. So this is the gal code, and I'm looking at U. The opcode is 3.7, and that's not any of these. Oh wait, this is 3.7. Yeah. Oh, you know what I did? I forgot to specify what domain this signal changes in. That's my bad. All right. Let's pull up command. Yeah, opcode is 7 bits. The bottom 2 bits are always 1 in the spec. So, all right. Command line. Let's try it again. Hey, I like this game. Okay, that worked. Let's try another short instruction. AUIPC. This is taking longer for some reason, but it worked. Okay, that's 2 down, a bunch to go. So what I would do now is I would just run all of the instructions. That's going to take 13 or so minutes. So let's get it started. Let's start it with 8 processors. Some of them are going to complete quicker than others. And my 13-minute estimate is from when I didn't have the chips in. So anyway, I'll just get things started. Let's see, what else can we do? So these are all the shards that I basically sharded things into. So all the loads in the stores are all separate verifications. There's fatal, which is for fatal conditions like misaligned addresses. There's interrupt requests, the various jumps, CSR, eCall and eBreak, beer break and coffee break, op and op-im, and the upper immediates. So how are things doing? Is it happy? It's pretty happy so far. So time, yes, okay, sure. Time make minus J8. That's right. I always forget to add time. Yep. Okay. Excellent. I didn't waste too much time. I wasted maybe a minute. That's okay. Okay. Let's see. What else can we do? Well, I'm not going to mess with the code. Let's take a look at KiCad again. So this is what we built. This is what we built in software. And it was a little painful, again, because we had to map abstract signals onto real chips. So that was kind of painful, but, you know, if formal verification works, it works. And that means that I can, you know, be assured that if I build this using the real circuit, using real chips, time passes. Yep. Wait. Time passes. Well played. If I build this using the real chip, I can be pretty assured that at least this section of code is going to function correctly. Again, modulo any timing issues. So that's pretty cool. Let me show you the level above this. Wow. This is pretty cool and a little small, but hopefully. How are things doing? Let me just take a quick peek. Things are pretty happy so far in formal verification land. So this is sort of like the top level of the sequencer. You can't really see it, but up at the top, these are some CSR registers. There are 7 of them that I had to stuff into the sequencer, and this was just so that I could handle interrupts and exceptions. So I stuck those up there. They have some multiplexers, so they get multiplexed and then multiplexed again because their outputs can go onto the X bus right over here. So that's the multiplexer. So when I looked at the code, I saw that the X bus could get data from any one of 3 places. It could get data from the PC, it could get data from stored memory, or it could get output from one of the CSR registers. So yeah, so rather than making a 7-input multiplexer, I just broke it up into 2 4-input multiplexers because that's what I had lying around. Maybe I'll change that. I don't know, but that's the CSR. So basically, what I did was I went through all of the code, and I looked at what got multiplexed onto each bus. And these are the multiplexers that I came up with. So for the most part, they're all 4-input multiplexers. If you ignore the whole CSR multiplexer thing. So that's kind of nice. This one down here, this one right here is, oh, the doorbell rang. I'll bet that's a package. It can wait. We don't really get porch pirates around here, he said. Hoping that there were actually no porch pirates. Well, anyway, so RD, this is the multiplexer for the destination register number. So it can either be the destination register or source register 1 or 2 from the instruction, or it could be 0, in the case where I don't want to write to a destination register. So that's what these multiplexers do. And then over here, you can see some of the internal registers that I've started laying out. So this is the PC, the program counter. This is the memory address. So this is the data if we write something to memory. And this is just a temporary register, which I found that, get my package, it might be cake. I'm pretty sure it's not cake. You want me to get my package? Fine. I'll get my package and I'll leave you with this. Okay, I got my package. Yeah, let's turn this into an impromptu unboxing session. Maybe you can see those, but those are spray tops and glass models. Why, you might ask, am I getting spray bottles? Because I have a Madagascar hissing cockroach as a pet, and they require high humidity. So this is a spray bottle that I can fill with water and then just spray his container and increase the humidity. Yeah, I've got this smoking humidifier, and it doesn't humidify the entire room, so I need to mist his cage every so often, so that's why I got this. Unboxing over. Oh, and I didn't get the plastic ones because I felt like splurging. And I felt that, maybe the plastic would degrade in the sunlight, so I got some glass bottles. I think I paid like $10 for it. Anyway. So, okay, so these were the internal registers, and the internal, internal registers. And the internal registers could get their data sourced from different places. So again, we've got some more multiplexers. This is kind of a theme of the entire circuit. I wanted to build the whole thing out of as many multiplexers and buffers and registers as I could. Because that's really easy. At least not the green face, yeah. Jim Carrey, man. I like him and I hate him. I like him because, you know, he's funny, but sometimes, you know, he's a little bit over the top. Many times he's over the top. I mean, he's just like, you know, out there. Anyway, enough of that. Let's see. So this is what I laid out so far for the sequencer. So things like the register card and the shifter card, those are pretty straightforward. But the sequencer is like, what is the name of your cockroach? His name is Hamster. Why? So that I can ask people if they want to see my hamster. Okay. Oh, Dumb and Dumber. Don't even get... I did not watch that movie because to me, watching people be dumb is not funny. So, I just don't find it funny. I just find it pathetic, actually. Anyway, don't get me distracted. Okay, so the sequencer is the most irregular of the circuits that I'm going to build. So things like the register card, the shifter card, what else is there? What else was there? I'm missing one of the cards. Wow, I'm drawing a blank. The ALU card, right? So those are more regular in that, you know, for the most part, they're just a bunch of buffers and then, you know, the actual chip functionality. So just go outside. No politics in the chat, guys. No politics in chat. I did kind of want to get started with the sequencer card first, just to see what things would look like, and to get started on a little more interesting circuitry. The other thing is that you can see that, you know, we've got these basic modules here. So we've got like a 4-input 32-bit multiplexer. So if I can build a little module that is a 4-input 32-bit module, you know, maybe I could just build a bunch of them and you know, maybe stick cards or something like that. Yeah, the shifter is definitely a bunch of buffers. It's all buffers, basically. So, yeah, memory card, yeah. I haven't even designed that yet, but I have the memory interface, so as long as it conforms to the interface, it'll be fine. Oh, and that's another thing. I'm planning on using static RAMs because they're cheap. You know, it's a 32-bit machine, which means that at most I will have 4 gigabytes of memory. Unless I do things like, you know, have processes, but I don't because I don't have a supervisor mode and I don't have a user mode. I just have a machine mode. So I'm doing bare metal programming. So the most RAM I can ever have is 4 gigabytes, and, you know, SRAM of that size is, well, maybe not easy to find, but I don't have to go the route of dynamic RAM, which I absolutely hate because you need refresh circuitry and it's slower. Static RAM is faster, so whatever. I probably won't need 4 gigabytes of static RAM, you know, maybe a few megabytes. Good enough. So anyway, so there are these little modules, there are these multiplexer modules, and there are these you know, register modules, and you know, maybe I could build you know, one circuit for each of these and then just, you know, duplicate them, and then somehow, I don't know, be filled with winning or something. Yeah, all the buffers is propagation delay. That's why I decided to use the FCT series. So we're talking about a propagation delay of something like 5 nanoseconds. So if you multiply that out by, I don't know, 10 levels, That's 50 nanoseconds, which still is within my 10 megahertz, which is 100 nanosecond target. So, yeah. The KiCad schematic is not generated from the code. This is totally manual. So I created these symbols, and then I'm just, wiring these up. This isn't even a valid schematic. This is just sort of like, sketching with pen and paper. So yeah, then once I am able to formally verify everything, then I will actually design some actual circuits. Let's go to the command line. See what's going on. It's still going. It hasn't listed out the results yet. It just looks like it's hung because it's actually, where is it actually waiting? I think this is the last thing it's doing, waiting for solver for fatals. Fatals always took the longest to verify because they actually test every instruction. They don't test the results of the instructions, which the other shards do. This just tests if an instruction goes fatal, that fatal exception handling actually happens. So, and unfortunately, it takes the longest amount of time, and it's only been 5 minutes or so. Sorry, 12 minutes. So, a little more. So let's go back to what? KiCad? Yeah. Okay. So this is what the sequencer card looks like. Here is, right over here, is the immediate decode hierarchical sheet. So if I click into that, that's what that is. And then, of course, each one of these is one of these 32-bit buffers. So already I'm beginning to break this up into chips. So there's the FCT series chips. Why are the 3 second-tier multiplexers on the left duplicated? Yeah, they have identical inputs but not identical outputs. So if I go up to the top, okay. So this is the register number for the X bus, the register number for the Y bus, and the register number for the Z bus. So the way it works is that when there is a register number present on one of these 3 buses, the register card puts the contents of that register onto the X bus or the Y bus. And if there's a Z register present, it loads that register number with the contents of the Z bus. So that's why there are 3 multiplexers, because I need to specify 3 registers, 2 source registers and a destination register. And these come from the instruction RD, RS2, and RS1. Sometimes they need to be swapped around. Sometimes you write to the destination register, and then on the next machine cycle you read from the destination register, or vice versa. So that's why they all get pretty much the same input, with the exception of this other one, which is sometimes I don't want to read from a register, or I want to load the bus with 0, which is what register 0 is. So that's that. Okay, so what was I going to do? Oh yeah, so here's the instruction decode. So if we looked at the code, let's take a look at the code. Where is sequencer card? Where's the instruction? Okay, so here's the instruction decode. Really all it is rewiring the instruction, right? So what that looks like in the circuit itself is this. I mean, there aren't any chips. It's just, a strict wiring job. So all I'm doing is basically renaming the bits of the instruction signal into the bits of these other signals. So that's all that is. And again, this isn't a valid schematic. These net names are probably all wrong, and they would probably completely fail design rule checking and electrical rule checking. Again, this is just to map things out so that, when I'm ready to do the real thing, I know where all the signals are supposed to go. Yeah, your bag of GAL 20 V8s, you should definitely do something with them. Probably the most canonical project to do with a GAL is to make a 4-bit binary to 7-segment decoder. That way you can display the digits 0 through 9 and A through F with a GAL. The thing about GALs is that there are some packages on GitHub. One is written in C, one is written in Rust to actually generate the bit streams. You still need a programmer. Supposedly the TL866-2 II can do it. I haven't actually tried it yet. The last time I tried it, it failed miserably, but that was 2 years ago. So, and from what I understand, they updated their algorithms. So, yeah. Cold coffee. How are you all doing in the chat? You all doing good? I hope so. Let's take a look at the command line again. We're still waiting for the solver. We're still waiting for the solver. It's been 17 minutes. May take a while, but at least everything else passed, which probably means that Fatal is going to pass because the only thing that I changed was the immediate values. So yeah, I think we'll just let this finish. Let's see what else we can do. VS Code, whiteboard. I can draw something. What do you think it's going to be? Yeah, I think we know what it's going to be. It's a cat. This is the cat circuit. It takes X and knocks it off the table. There's not really much else that I wanted to do today. I really want the formal verification to finish up. And basically, this is what I wanted to accomplish today. I did want to take a small part of the circuit, a relatively simple part of the abstract logic, and convert it into real chips. And then rerun formal verification to prove that my mapping from abstract logic into real chips does actually work. And so far it looks like it did. So that was a pretty neat accomplishment. So yeah, and we did that basically. Basically, I am able to go back and forth between the chip version and the abstract. So basically, I'm able to go from the chip version to the abstract logic version back and forth if I need to, simply by setting this Boolean up. Okay, I think we're done. We are done. We have pass on everything. So this column here is the number of seconds that it took. So we can see that Fatal took 1,200 seconds, which is something like 17 minutes or so. In fact, it says it 20 minutes. Okay, 20 minutes. So LUI, being such a simple instruction, only took 13 seconds. AUI PC took 34 seconds. So most of these things, took something like under 5 minutes to do. Unfortunately, Fatal takes way too long. Would there be a way we can donate CPU power to help verify? Well, no. I mean, there's a long pole here, and the long pole is fatal. I could, I suppose, break up fatal into checking different sections of the instruction space. I could divide it into 4, maybe. I could do that and just call it fatal 1, 2, 3, and 4. And then it should pass in a quarter of the time. So, you know, maybe I'll end up doing that. So you can see that the in real time it took 20 minutes total. So, so if I actually eliminate fatal, if I actually eliminate fatal as the long pole, what's the next longest pole? It looks like IRQs and op. So, you know, and then it'll take something like 7 minutes or so, which is fine. So, yeah, I guess that's all I wanted to do. All right, I'm not a professional streamer, so I don't have a stream close video. I only have a stream open video that I made this morning. So I guess that's about it. I hope you enjoyed listening to me waffle on about electronics and coding and formal verification and unboxing glass bottles for hissing cockroaches. And I will probably be doing more streaming because it is the end of the year and I am pretty much off for the last 2 weeks of the month. So this is a vacation. So I can stream and do other stuff, and hopefully you can put me in the background because, you know, listening to every single word I say, you know, it's you can either do that or you don't have to. I often like to listen to other people just do work in the background, so it's sort of like, you know, I'm around other people doing work. So, and I'm okay if you do that too. So, I guess that's about it. Thanks for watching. Hope to see you on the next stream. And remember, you're hardcore. See ya.